In this video, we're going to implement a function to approximate the Lyapunov spectrum, so to compute all Lyapunov exponents of the Lorenz system using the automatic differentiation engine in JAX. Let's get started. The channel sponsor Pasteur Labs is currently hiring SciML and software engineering positions. Check out pasteurlabs.ai/careers for more details. Hi and welcome to this new video where we're going to approximate the Lyapunov spectrum of the Lorenz system. Recall this Lorenz system was a prototypical example of so-called deterministic chaos. That means that the trajectory is very sensitive to the initial condition. And typically the exponential error growth from a slightly perturbed initial condition is given in terms of the largest Lyapunov exponent, which is what we approximated in one of the previous videos. But for a dynamical system of n degrees of freedom, so here in case of the Lorenz it has 3 degrees of freedom, there are as many Lyapunov exponents and they together form the Lyapunov spectrum. And we can use the entire Lyapunov spectrum to compute some informative quantities about the dynamical system. So for instance, the Kaplan-York dimension, or we can also analyze properties of the dynamical system based on the sign of these Lyapunov exponents. So we're going to implement this approximation function. For this, we will again use the Lorenz system in the default configuration from the original Lorenz paper, with an explicit Runge-Kutta 4 integrator and a delta t of 0.01. And then we approximate the Lyapunov spectrum consisting of these 3 Lyapunov exponents using the following strategy. Again, we need to first get on the chaotic attractor, so on the butterfly shape. For this, we will draw a reasonable initial condition and then warm it up for some time steps. So here I just used 5000 and then we are pretty sure to be on the chaotic attractor. And then in contrast to the previous video in which we then introduced a small perturbation, we now need a perturbation matrix which is of size degrees of freedom by degrees of freedom. We can initialize it using drawing individually from a normal distribution, but then we need to orthonormalize it such that the columns form a basis, and we can use a QR decomposition for that. You could also use a stabilized Gram-Schmidt method, but I think the QR decomposition here is just fine. So we will QR decompose the Y0 matrix, and then we can use the Q matrix as the new Y matrix. And this is basically our initialized perturbation matrix. And then the most important part of our routine is to evolve a trajectory on the chaotic attractor using our Runge-Kutta 4 simulator, where in each time step we will of course advance the state in time. So we will use our time stepper, here denoted as calligraphic p, to advance the state from ut to ut plus 1. And then at the same time we will evaluate the Jacobian of the evolution mechanism. So we will use the automatic differentiation engine of JAX to compute the Jacobian of the propagation procedure. And then we can advance the perturbation matrix in time by multiplying it with the Jacobian. But then after this multiplication, we do no longer have an orthonormalized matrix. And so we will re-orthonormalize it in each time step. So we will take our Y matrix at t plus 1, QR decompose it, and then override the Y matrix with the Q, so with the re-orthonormalized. And then we're going to use R, which is in the QR decomposition, the upper rectangular matrix. And on its diagonal, we will record growth factors. And this is basically can be interpreted as each of these bases that the Q matrix or the Y matrix are made up, how much they grow in each time step. And this evolution procedure we will do for a bunch of time steps. So here 50,000 is a good order of magnitude. And in each time step, we will record these growth factors. At each time step, the growth factor is a 3-dimensional vector. So we will then get a trajectory of 50,000 entries of 3-dimensional vectors. And then we can approximate the Lyapunov spectrum by taking the element-wise mean of our trajectory of 3-dimensional vectors, taking the element-wise natural logarithm, and then computing the mean over the trajectory axis. Then essentially we can further divide by delta t, which is like to get the Lyapunov exponent in physical time, and this then basically gives us our 3 different Lyapunov exponents. This is what we're going to implement. First, we will make a more naive implementation with a dense instantiation of the Jacobian matrix, and then I will show you a way to do this more efficiently in JAX using automatic vectorization and the automatic linearization of functions. So then let's get started with the coding, and let me get down here. So we will need JAX and JAX NumPy, and then we will again use the Runge-Kutta 4 simulator that we implemented in a previous video. If you want more details, I will have the video linked up here. So we will define the right-hand side and then this numerical integrator, which we can instantiate it. And then it essentially takes a 3-dimensional vector and maps it to the next state in time. So for instance, if we started at the ones vector, we now have another 3-dimensional vector representing the next state in time. Then also in the previous video, we implemented an efficient autoregressive rollout using JAX scan, and we implemented it as a function transformation. And this can be used to produce a trajectory. So here with these 5,000 time steps, but since we are only interested in warming up the state, we only need the last entry. So then we can get down to business and implement the actual routine that pushes these growths through the trajectory. So let's implement a function and let's call it the push orthonormal matrix variation. So it's a bit of a mouthful. And this basically takes a stepper. So this is the function which advances from one state to the next. Then we need an initial state. We need the initial perturbation matrix. And we also need to know for how many steps we're going to push these perturbations. And then, similar to what we have here with the rollout, we're going to use JAX scan as an efficient way for autoregressive rollout, because that pushes the for loop into the JAX compiler, and then this runs like very efficient also on CPUs. The only difference is I don't want to implement this as a function transformation, but as a function which directly executes this rollout. So we will need to implement a scan function for this. So let's implement the scan function, and the scan function takes in a carry and an additional forcing term, and then produces the next carry as well as the term that's going to be stacked. So here we don't have any forcing. The only thing we have is a carry, and essentially if we go up to our mathematical description, we see among or between 2 iterations, what needs to be carried is the state, so this 3-dimensional vector, as well as the perturbation matrix, which is this 3 by 3-dimensional matrix. So the carry can then be destructured into a u and a y by unpacking the carry, and then we can integrate u to u next by calling the stepper on u. So this is basically the regular integration. Then we need the automatic differentiation engine to produce the Jacobian. So we can produce the Jacobian by doing jax.jack forward on the stepper evaluated at u. So jack forward is a function transformation, takes in a function which goes from 3-dimensional to 3-dimensional vector, produces a function that goes from 3-dimensional vector to 3 by 3-dimensional matrix, and we will evaluate the Jacobian at this previous state in time. And then we can push forward the perturbation matrix y by left multiplying the Jacobian, matrix multiplying the Jacobian to y. So this already pushes both the state and the perturbation matrix to the next time step. Then we need to re-orthonormalize. So we're going to say q, r is jnp.linalg.qr on y next. And then we can just override y next is q. So because we're going to have it re-orthonormalized. And then importantly, we will have this R matrix, which is an upper rectangular matrix, but we're only interested in its diagonal entries. And let's call them the growth factors. And those can be extracted by doing jnp.diag on R. Then we can assemble the next carry. So carry next. And this is just simply a tuple with u next and y next. And then essentially in the next iteration, when the scan function is applied, it can be unpacked again. And then this scan function shall return carry next, and growth, because the second returning variable is going to be the one that will be stacked. And that's what we're interested in. We're not just interested in one but growth factor, but in these 50,000 growth factors. Then let's use JAX-scan. So JAX-scan. If you want more intro to JAX-scan, I also have a video linked up here. It's an extremely handy function. I like it very much. It pushes, as said, this for loop into the compiler, has these auto-regressive rollouts run extremely quickly. Very, very handy. So we need a scan function, which we're going to happily provide. We need an init. Okay, we need to initialize. So we need an initial carry. Makes sense, right? We need a point to kick it off. We have our initial state and we have the initial perturbation matrix, but according to our algorithm, we also need to orthonormalize the initial matrix. If it is already orthonormalized, that's fine, but just to be sure, we're going to do another QR decomposition. So let's do Q and then use an underscore because we're not interested in the rectangular matrix with the initial perturbation matrix with JNP linalg.qr on y0. And then we can essentially build the initial carry as a tuple with u0 and q. This can then be provided to JAX-scan as the initial carry. Then there is another argument allowing us to provide the forcing trajectory, which would be supplied as this second argument to the scan function. But here, because we don't have any forcing, we can say none, and that's more than fine. And then we need to define the length, which is going to be n, because we want to have, in our case later, 50,000 rollout steps. And then this JAX-scan returns two things. It returns a final carry, so the final state and the final perturbation matrix, which we're not interested in. So let's use a placeholder for this. And then we have the growth trajectory, which is what we want and can ultimately return as part of this function. Then let's use this freshly baked function. So for this, we also need to draw this initial perturbation matrix. So let's do a y0 and just have it, let me scroll down a bit, as jax.random.normal on jax.random.key and just use some random key, for instance 0. And then we instantiate a 3x3 dimensional matrix. Let's take a look at it. And this is just a random matrix. There's a chance that it's orthonormal, but it very likely is not. So this initial orthonormalization is quite helpful. Then we can record or get the growth trajectory by calling our just defined function. So push orthonormal matrix variation, and we're going to use the stepper that we instantiated. As u0, we're going to use the warmed up state, and then we will use our perturbation matrix, and let's do 50,000 time steps. This takes a while, but because there's some JIT compilation happening, but rerunning it should only be a second. Let's take a look at the shape. So this growth trajectory has 50,000 dimensional in the 0th axis and then 3-dimensional in the latter axis. So it has these 3 growth entries associated with the 3 Lyapunov exponents across 50,000 time steps. Okay, then we go up to our formula. So essentially what we have to do is we have to take the element-wise absolute, the element-wise natural logarithm, and then compute the mean over the trajectory axis. So let's call this the unscaled Lyapunov spectrum. And this is essentially jnp.mean applied to jnp.log for the natural logarithm on jnp.absolute on the growth trajectory. And then the mean should be applied only over axis 0, because axis 0 is this temporal snapshot axis that we want. And then let's take a look at its shape. That should now only be 3-dimensional. And we can investigate it and see we basically get 3 numbers. 2 of them seem to be negative, and we have 1 positive number. Here right now, we still have, and that's also the reason I call it unscaled, we have a Lyapunov spectrum which assumes a delta t of 1, but our delta t of the Lorenz stepper is 0.01. So we're going to divide by that, as we also have it here in the formula, to get our true Lyapunov spectrum. So let's do that. The Lyapunov spectrum is going to be the unscaled Lyapunov spectrum divided by the Lorenz stepper dot delta t. And let's take a look at that one as well. And I think since we usually don't have these super high precision here, we can probably round it to 3 significant digits. And then essentially we see our Lyapunov spectrum. Here it is also ordered. So we have a positive 0.904, then we have approximately 0, and then we have minus 14.56. And this is also the Lyapunov spectrum you would expect for the Lorenz system in the default configuration. This very left quantity, so the 904, or this 0.904 because it's 10 to the minus 1, is also what we computed in the previous video. The true Lyapunov, or the largest Lyapunov exponent usually found to the 4 significant digits after the comma, is at 0.9056. So we are a little bit off, but that's typical when you approximate Lyapunov exponents or Lyapunov spectra. So you might need to use a meta strategy with using different initialization and then redo the computation to get a more precise estimate. But here we are correct up to 2 digits after the comma, which is for most analyses more than fine. Then we have the 0 Lyapunov exponent and a negative Lyapunov exponent. Typically, a positive Lyapunov exponent is associated with chaos. That's also the reason when the largest Lyapunov exponent is positive, we do have chaos. But the entire spectrum describes the kind of dynamics we see and other properties. So for instance, since our second Lyapunov exponent is 0, we have a 0 Lyapunov exponent, meaning that our system is to some extent stable. And then we have a negative Lyapunov exponent, which balances out with the positive Lyapunov exponent and creates the fractal structure that we see in the butterfly shape. So the last thing I promised is to implement a more efficient way of the growth perturbation, or the perturbation growth. And here I said we directly instantiated a dense Jacobian matrix and then performed a matrix multiplication. This can be done more efficiently by using the lower level primitives of automatic differentiation within JAX. So let me add a comment here and call this the Jacobian instantiation approach. It's not wrong, instantiation, but it is a bit inefficient. And let me comment it out. And now we're going to use a more efficient approach. And for this, we will use JAX.linearize. JAX.linearize is basically working similarly to how JAX.VJP would work, so the vector Jacobian product, but for forward mode autodiff. I will have a video for this linked up here. So when you think about forward mode, you would think about Jacobian vector products, but the way JVPs are implemented in JAX is that they both push the primal and the tangent forward, which makes sense because you can do this alongside, but they don't return a linearized or a function that would do the propagation on the tangent. And that's what linearize is for. So here we will apply linearize to the stepper at u, and this basically gives us u next and a Jacobian vector product function. And this Jacobian vector product function can then be applied to a tangent vector and would thereby have it be pushed like it were a matrix multiplied with a Jacobian from the left. Okay, long story short, now we can use this JVP fun to push y to y next by applying JVP fun, but this will not work because the Jacobian vector product function expects the input to be of the same shape as the primal input, and the input to the primal, or the input to the stepper, is a 3-dimensional vector, and now we want to apply it to a 3 by 3-dimensional matrix. And so we will use JAX.vmap to vectorize its application and have it perform on matrix or 2-axis array inputs. But we also have to be careful here. The default option for VMAP is to vectorize over the 0th axis. So if we have a matrix, it would vectorize over the rows. But our concept here that we're using is that we have the typical linear algebra convention that if we have a basis matrix, an orthonormal basis matrix, which we will get after the QR decomposition, the basis vectors are in the columns. So they're not in the rows, but they're in the columns. So we need to vectorize over the columns. So we're going to say in axis, so basically this is the axis to vectorize over, is -1, because -1 is indexing it from the rear. So this is basically as if we were to plug in 1. And we also need to define the out axis. And then essentially that works as if it is vectorized over the column dimension or column axis. So we can then re-execute that one and recompute our spectrum. So the values have ever so slightly changed. That's of course, there can be some smaller rounding error differences, but they should be negligible, as we also see here. If we then round up to 3-digit after the comma, we still get this positive Lyapunov exponent, we get the 0 Lyapunov exponent, and we have this negative Lyapunov exponent. And the advantage of the approach I just showed you is that it is more efficient if you then had larger system or larger dynamical systems, for instance those that would come from the discretization of a partial differential equation. This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed this video. If you did, then please leave a like and consider subscribing to the channel. There's more cool content about dynamical systems, emulating dynamical systems with neural networks, and analyzing their performance. Here you will now see similar videos, and I hope to see you in one of the next videos.